All right, here we are for Math Tidbits number 3. So this is going to concern the components of vectors and writing vectors in component notation. All right, so vectors and vector components. All right, the concept of vector components is not terribly complicated. And really, the breaking up of vectors into their components and also expressing vectors in component notation is not terribly difficult conceptually, although, again, for many, the experience in high school didn't necessarily include doing much with formal component notation for vectors. So if we go ahead and bring out our old friend vector A again, where the angle theta here is the angle above the horizontal, and we'll use usual Cartesian coordinates x and y, and then finally label the vector as vector A. The components that you are likely familiar with would be these, where we would label this as a sub x and this is a sub y, the extents along the two coordinate axes. The magnitude, of course, of a is equal to the square root of ax squared plus ay squared. Thank you, Pythagoras. All right, we might write down one of the ways to express the vector as in terms of its components would just be an ordered pair, ax comma ay between parentheses, right? Or if you want, if there's a three-dimensional version, we would just have ax, ay, az. So that's perfectly sound, perfectly solid way to express the vector in terms of its components. And if two vectors are equal, so let's suppose there's a vector b that's equal to vector a, then that means that all of its components, a sub x and a sub y and a sub z, every one of them is identical, right? Okay, so that's all well and good. Hopefully this idea is something that is familiar to you, or if not, it will be. One of the things that we don't often think about, but is extremely useful in physics, is the idea that a vector is a vector, no matter how small. Where does that come from? Must be Horton Hears a Who or something like that. Anyway, a vector is is the same regardless of the coordinate system that you might be interested in talking about, right? So here's my vector A, right? That vector is a vector in space. And the coordinate system that we use doesn't change the nature of the vector. What it will change is the coordinates, or it will change. What it will change is the components in various directions. So let me explain this by a pair of different axes. So here we have system number 1 with the x and y axes labeled like so. What if we instead decided to use a rotated coordinate system? X prime and y prime, like that. You should, as you look at this, recognize that vector A will be written as ax comma AY in the first system, I want to call it the unrotated system because honestly, how do you know which one is the rotated coordinate system? You really don't, in fact. You can't call one the rotated coordinate system and the other the non-rotated coordinate system because they're rotated with respect to one another. What about vector A as written in the primed system? I don't even want to call it A prime because it's vector A, right? But vector A in that coordinate system will have those components. It's not going to even have a y component because of the choice of rotation that I made in situating the primed coordinate system relative to the unprimed coordinate system. So these two expressions for A nevertheless reflect the fact that it is one vector. They are the same. This is not to say that AY is 0 or AX equals AX prime. That is not correct, as you will learn as we work with vectors and various coordinate systems. But I did want to point out that use this to point out that a vector is what it is, regardless of the coordinate system in which it is represented. All right, so in terms of our just using this simple vector notation as an ordered system of x, y, and z components, let's think about what scalar multiplication means. Well, if I take A as defined above, and I want to now make a vector D equal to C times A, then what that will be represented as is CAX, CAY, CAZ. The C gets distributed throughout. Okay? So that then you would say something like dx is equal to C times AX, and so on. Okay? So when I do a scalar multiplication, I simply multiply the scalar by all of the components. That's pretty straightforward. How about adding things together? Well, let's say vector G is equal to vector A plus vector B. Again, as you might expect, I simply add the components together. AX plus BX, comma, AY plus BY, comma, AZ plus BZ. And so, for addition or subtraction, I simply do what comes naturally, as it were. I take and I subtract the various components, or add the various components, if addition is what I'm doing. Okay? Right. Well, that's one way. One of the ways which we have to express vectors in terms of their components. The other way, and this is the way which we will find more useful, I believe, is to utilize the concept of the Cartesian unit vector. So I mentioned this in a previous video, that if I were to take my three axes, x, y, and z, and take vectors which are unit length in each of the three directions, I have another system for representing vectors by components. So the convention that we will use, and is most commonly employed in physics, is to use I hat, J hat, and K hat. You can remember the order, it's just alphabetical. I hat, J hat, and K hat to represent unit vectors pointing in the three orthogonal Cartesian directions. Sometimes people use x hat, y hat, and z hat. I believe that's can be confusing, so I want to use this particular convention that I hat, j hat, and k hat represent unit vectors in the x, y, and z directions respectively. Now, if this is done, then vector A is represented as a sub x times I hat plus a sub y times j hat plus a sub z times k hat. So this little guy is the component of A as a vector. So this is the vector component in x direction, in y, in z. So that if you were to draw this out, I guess, if vector A is in some direction like this, then here would be the part we have called ax I hat, and here would be the part we have called a y j hat, and here would be the part we would call a z k hat. And those three added together represent the three components of that vector. All right. So it's kind of hard to visualize three-dimensional things in a two-dimensional space. So we could perhaps better review this by taking vector A as just ax plus ax comma, sorry, ay, a two-dimensional vector. We represent that vector also as ax I hat plus ay j hat. And here are my x and y axes. And here is vector A. And then now here is the part that we call ax I hat. And here is the part that we call ay j hat. So the hats, the unit vectors, just give the direction of that part, and the magnitude of that part is ay or ax and ay respectively. And you can see right off, just looking, we've reproduced the graphical notation, right, or the graphical addition, tail to tip, ax I hat plus ay j hat equals a. That is all this thing represents. The geometric addition of those two portions, the portion of the vector in the x direction and the portion of the vector in the y direction. Okay? When we add two vectors, so let's imagine that we bring in another vector b equal to bx I hat plus by j hat. Then when I want to take vector A plus vector B, just as before, all we need to do, let's just write all of this out. This will be ax I hat plus ay j hat plus bx I hat plus by j hat. Now we can group together like terms. Okay, so the part that's in the x direction is ax plus bx, and the part that's in the y direction is ay plus by. And then this, if you like, if that's vector c, we could call this component cx, and this one cy. Okay? So, we will often work with this notation so that it's familiar to you. I want to discuss in the next video the scalar and vector products using this notation. Now, that will be very important. It'll also provide some important insight to some of the things we've been talking about. Okay, so next up, products of vectors in component notation. All right, see you next time.